Mercury is the closest planet to the Sun. It's right there, closer to us than Mars, closer than Jupiter, closer than any of the outer worlds we've spent billions exploring. On a clear evening, just after sunset, you can sometimes see it, a bright point of light hovering near the horizon, visible for just a few minutes before it sinks below the edge of the world. Ancient astronomers tracked it for thousands of years. Every civilization that watched the sky knew this quick-moving wanderer. And yet, for 30 years, 3 entire decades, NASA didn't send a single spacecraft to visit it. Not one. Between 1975 and 2004, humanity completely ignored the smallest planet in our solar system. We sent missions to Mars, to Jupiter, to Saturn, to Uranus, to Neptune. We landed on Venus. We flew past comets and asteroids. We explored the outer reaches of the solar system. We sent rovers to crawl across Martian soil. We dropped probes into Jupiter's crushing atmosphere. We photographed the geysers of Triton and the volcanoes of Io. We discovered new moons, new rings, new worlds. But Mercury? Nothing. Radio silence. Total neglect. For 30 years, the closest planet to the Sun received less attention than asteroids, less attention than comets, less attention than moons of distant gas giants. Why? What made this tiny world so difficult, so expensive, so seemingly impossible to reach, that the most powerful space agency on Earth simply gave up for 3 decades? The answer involves orbital mechanics, budget politics, scientific priorities, and one of the strangest planets in our solar system. A world that defies expectations at every turn. Tonight, we're going to uncover the truth. We're going to explore Mercury's extreme temperatures, impossible geology, and mysteries that scientists are still struggling to explain. And we're going to understand why getting there is one of the hardest things humans have ever attempted in space. Stay with me. This story is stranger than you think. Let's start with a basic question. What is Mercury? Mercury is the smallest planet in our solar system, just 4,879 kilometers in diameter. That's only about 40% larger than our moon. If you placed Mercury next to Earth, it would look like a tennis ball beside a baseball. In fact, Mercury is smaller than 2 moons in our solar system: Ganymede, the largest moon of Jupiter, and Titan, the largest moon of Saturn. Both of these moons exceed Mercury in diameter. Mercury is a planet only because it orbits the Sun directly, not because of its size. It orbits closer to the Sun than any other planet, at an average distance of about 58 million kilometers. That's less than 40% of Earth's distance from the Sun. At its closest approach to the Sun, called perihelion, Mercury comes within 46 million kilometers. At its farthest, called aphelion, it reaches about 70 million kilometers. This orbital eccentricity, the degree to which the orbit deviates from a perfect circle, is the highest of any planet except for the now demoted Pluto. Mercury's orbit is noticeably elliptical, which has important consequences for its climate and its strange day-night cycle. And it moves fast. Mercury completes one orbit in just 88 Earth days, racing around the Sun at an average speed of 47 kilometers per second. That's nearly 60% faster than Earth's orbital velocity. It's the fastest planet in the solar system, which is why ancient Romans named it after Mercury, the swift-footed messenger of the gods. The Greeks had 2 names for it: Apollo when it appeared in the morning sky, and Hermes when it appeared in the evening. They didn't initially realize these were the same object. It was only later that astronomers understood this quick-moving point of light was a single planet racing around the Sun on the innermost track. From Earth, Mercury is notoriously difficult to observe. It never strays far from the Sun in our sky, appearing only briefly after sunset or before sunrise, low on the horizon, obscured by atmospheric haze. Even at its greatest elongation, its maximum angular distance from the Sun, Mercury appears only about 18 to 28 degrees away from our star. This means you're always looking through a thick layer of Earth's atmosphere when you observe Mercury. The turbulence blurs the view. The dust and moisture scatter the light. Professional astronomers often joked that Copernicus, the great astronomer who proposed the heliocentric model, never saw Mercury in his entire life because of the poor horizon visibility in his native Poland. Mercury has no moons, no rings, almost no atmosphere, just a thin exosphere of atoms blasted off its surface by solar radiation and micrometeorite impacts. This exosphere contains sodium, potassium, oxygen, and other elements, but it's so thin that atoms rarely collide with each other. The pressure at Mercury's surface is about 1 trillion times less than Earth's atmospheric pressure. Its surface is cratered and ancient, baked by the nearby Sun, frozen in the shadows. It looks superficially like our Moon, grey, barren, covered in impact craters that have accumulated over billions of years. But Mercury is not like the Moon. Mercury is deeply, profoundly strange, and the more we learn about it, the stranger it becomes. Here's your first mystery. Mercury is way too dense. For a planet its size, Mercury has an absurdly large iron core. The core makes up about 85% of Mercury's radius, compared to about 50% for Earth. If Mercury were the size of a baseball, its core would be like having the entire ball made of iron, except for a thin leather covering. Let me put this in perspective. Earth's core is about 3,500 kilometers in radius, surrounded by a mantle and crust totaling about 2,900 kilometers. The rocky outer layers make up a substantial fraction of our planet. Mercury's core is about 2,000 kilometers in radius, but the mantle and crust together are only about 400 to 600 kilometers thick. The planet is essentially a giant iron ball with a thin rocky shell. This gives Mercury an average density of 5.4 grams per cubic centimeter, the second highest density of any planet in the solar system after Earth. But Earth's high density is partly due to gravitational compression. At the immense pressures inside Earth, rock is squeezed into denser configurations. If you could somehow decompress both planets, expand them to their uncompressed volumes, Mercury would actually be denser than Earth. Mercury has more iron per unit volume than any other planet we know. This is bizarre. No other rocky planet has proportions like this. Mars has a relatively small core, perhaps half its radius. Venus and Earth have moderate cores. Mercury's core is enormous. Why? We don't know for certain. One hypothesis suggests that Mercury was once much larger, perhaps twice its current size, but a catastrophic collision early in its history stripped away most of its rocky mantle, leaving behind the dense iron core with just a thin shell of rock. This giant impact hypothesis is similar to how we think Earth's moon formed. A Mars-sized object struck the early Earth, ejecting debris that coalesced into the moon. Perhaps Mercury experienced something similar, but instead of forming a moon, the debris was lost to space, vaporized by the nearby sun, or scattered by gravitational interactions. Computer simulations show this is possible. A glancing blow from a large impactor could have stripped Mercury's mantle while leaving the core intact. The ejected material would have been mostly silicate rock, explaining why Mercury kept its iron but lost its lighter materials. Another hypothesis proposes that the intense solar radiation near Mercury's orbit affected how the planet formed, preventing lighter materials from accumulating, while denser iron was drawn in. In the inner solar system, temperatures were high during planet formation. Materials like water ice and volatile compounds couldn't condense. They remained as gas, blown away by the solar wind. Only refractory materials, rocks and metals that remained solid at high temperatures, could accumulate. Perhaps the conditions near Mercury's orbit favored iron accumulation over silicate rock. Perhaps iron-rich particles migrated inward, while rocky particles were pushed outward. The physics of planet formation is complex, and we're still working out the details. A third idea suggests that Mercury formed elsewhere in the solar system and migrated inward, experiencing processes we don't fully understand. Planetary migration was common in the early solar system. Jupiter and Saturn may have migrated significantly, disrupting the orbits of smaller bodies. Perhaps Mercury formed farther from the Sun, where conditions were different, and then migrated inward to its current position. The truth is, we're still trying to figure out why Mercury is so weird. And this is just the first mystery. Here's the second. Mercury has a global magnetic field. This shouldn't exist. Planetary magnetic fields are generated by the dynamo effect, convection currents in a liquid metallic core stirred by the planet's rotation. Earth has a strong magnetic field because our core is liquid and our planet rotates relatively quickly, once every 24 hours. The dynamo effect requires 3 ingredients: a liquid conducting material, like molten iron, convection, hot material rising, cool material sinking, and rotation to organize the flow into coherent patterns. Without all 3, the dynamo fails. Mercury rotates incredibly slowly. 1 Mercury day, 1 complete rotation on its axis, takes 59 Earth days. That's almost 2 months for a single sunrise to sunrise cycle. Mercury rotates about 60 times slower than Earth. With such slow rotation, Mercury shouldn't be able to generate a magnetic field. The dynamo effect requires rotation to organize the convection currents. Without sufficient rotation, the currents would be chaotic, unable to generate a coherent global field. Mars, for comparison, rotates almost as fast as Earth, once every 24 hours and 37 minutes. And yet Mars has no global magnetic field today. Mars may have had one in the past, but it died billions of years ago when the planet's core solidified or the convection stopped. If Mars can't maintain a magnetic field despite fast rotation, how can Mercury maintain one with almost no rotation? And yet, Mercury has a magnetic field. It's weak, about 1% the strength of Earth's, but it's there, it's real, it's global, and it's been confirmed by multiple spacecraft. Mariner 10 first detected the field in 1974, shocking scientists who expected Mercury to be magnetically dead. Messenger mapped the field in detail, confirming its existence and revealing its structure. Mercury's magnetic field is offset from the planet's center, shifted northward by about 20% of Mercury's radius. It's also asymmetric, stronger in the north than in the south. These peculiarities add to the mystery. How does Mercury maintain a magnetic field with such slow rotation? This remains one of the biggest puzzles in planetary science. Several hypotheses have been proposed. Perhaps Mercury's core has unusual chemical composition. Perhaps it contains sulfur or silicon that lowers the melting point, keeping more of the core liquid than expected. A larger liquid outer core might compensate for the slow rotation. Perhaps the dynamo operates in a different regime than Earth's dynamo, a thin shell dynamo, where convection occurs in a narrow layer rather than throughout the core. Simulations suggest such dynamos can operate at lower rotation rates. Perhaps the crystallization of Mercury's inner core releases light elements that drive compositional convection, providing the energy for the dynamo even without strong thermal convection. Something about Mercury's core, perhaps its composition, perhaps its thermal state, perhaps something we haven't thought of, allows it to generate a field that shouldn't exist. Stay with me, because it gets weirder. Here's the third mystery. Mercury has ice at its poles. Yes, ice, water ice, on the planet closest to the Sun. This seems impossible. Mercury's surface can reach temperatures of 430 degrees Celsius on the sunlit side, hot enough to melt lead, hot enough to melt zinc, hot enough to destroy most materials we use in everyday life. This is hotter than the surface of Venus, even though Venus is farther from the Sun, because Venus's thick atmosphere traps heat through a runaway greenhouse effect. At 430 degrees, you could cook a pizza in seconds. Aluminum would start to weaken. Electronic components would fail. Plastics would vaporize. It's a temperature that seems fundamentally incompatible with ice. But Mercury has almost no axial tilt. Its axis is nearly perpendicular to its orbital plane, tilted only about 2 degrees compared to Earth's 23.5 degrees. This tiny tilt has enormous consequences. On Earth, our axial tilt causes the seasons. In summer, the northern hemisphere tilts toward the Sun, receiving more direct sunlight. In winter, it tilts away. The Sun rises high in the summer sky and low in the winter sky. On Mercury, there are no seasons in this sense. The Sun's path across the sky doesn't change significantly over the year. And crucially, the Sun never rises high at Mercury's poles. If you stood at Mercury's North Pole, the Sun would always be at or near the horizon, circling around you but never climbing into the sky. The shadows would be long and permanent. Certain areas, particularly the floors of deep craters, would never receive direct sunlight at all. These are the permanently shadowed regions, places that have been dark for billions of years, places where sunlight has never penetrated since the craters formed. In these eternal shadows, temperatures drop to -170 degrees Celsius or colder. Without sunlight to provide energy, the only heat source is thermal conduction from the surrounding terrain, and crater walls are poor conductors. The shadowed floors become cold traps, isolated from the scorching heat just meters away, cold enough for water ice to survive indefinitely. Radar observations from Earth in the 1990s first hinted at ice deposits in Mercury's polar craters. The Arecibo radio telescope in Puerto Rico bounced radar signals off Mercury and detected unusually bright reflections from the polar regions, exactly the signature expected from water ice. The Messenger spacecraft confirmed them, mapping bright deposits that match exactly with the permanently shadowed regions. The spacecraft's neutron spectrometer detected hydrogen, a component of water, concentrated at the poles. The ice deposits are substantial. Radar imaging suggests they could contain up to 1 trillion kilograms of water ice, equivalent to a lake covering 20 square kilometers, 100 meters deep. Where did this ice come from? Probably comets and water-rich asteroids that struck Mercury over billions of years. These impacts would have delivered water to the surface. Most of that water would have been instantly vaporized by the impact and lost to space. Mercury's weak gravity can't hold on to water vapor for long. But some molecules, bouncing randomly across the surface in ballistic hops, would have eventually found their way into the cold traps at the poles. Once there, they became trapped. The temperatures were too low for them to escape. They accumulated over eons, layer upon layer, building up deposits that persist today. The ice appears to be covered in some areas by a thin layer of dark material, perhaps organic compounds delivered by the same comets that brought the water. This dark layer acts as an insulating blanket, protecting the ice beneath from the slight warming that occurs when sunlight grazes the edges of the shadowed regions. Ice on Mercury. The hottest planet in some ways, the coldest planet in other ways. A world of extremes that defies simple categorization. The same ice deposits may exist on the Moon, which also has permanently shadowed craters at its poles. Future explorers might use this ice as a resource: water for drinking, oxygen for breathing, hydrogen and oxygen for rocket fuel. Mercury's ice is too remote for near-term use, but it tells us something profound about the solar system. Water is everywhere. Even on the most hostile worlds, water finds a way to persist. Let me tell you about the first spacecraft to visit Mercury. Mariner 10 launched on November 3, 1973. It was a small spacecraft, weighing just over 500 kilograms, about the weight of a grand piano. Its mission was ambitious: use Venus as a gravitational slingshot to reach Mercury, the first spacecraft ever to use a gravity assist to travel to another planet. The gravity assist concept had been proposed by Italian mathematician BepiColombo, who would later have a mission named after him. Colombo realized that the gravitational pull of a planet could be used to bend a spacecraft's trajectory and change its velocity, essentially getting a free boost by borrowing energy from the planet's motion around the Sun. The gravity assist was essential. Without it, reaching Mercury would have required enormous amounts of fuel, more than any rocket of the era could provide. The problem, as we'll discuss more later, is that Mercury orbits close to the Sun and moves very fast. Matching its orbit requires shedding a tremendous amount of velocity. By flying past Venus and letting its gravity bend the trajectory, Mariner 10 could reach Mercury with the technology available. The gravity assist redirected the spacecraft onto a path that would intersect Mercury's orbit at just the right time and place. But Colombo contributed something even more valuable. He noticed that the trajectory could be designed so that Mariner 10's orbital period around the Sun would be exactly twice Mercury's orbital period. This meant the spacecraft would return to the same location every time Mercury completed 2 orbits, allowing multiple flybys with a single mission. The mission was a triumph of orbital mechanics. Mariner 10 flew past Venus in February 1974, using the planet's gravity to redirect its path toward the inner solar system. The Venus flyby also provided valuable scientific data, including ultraviolet images of Venus's cloud structure. On March 29, 1974, Mariner 10 made its first flyby of Mercury, passing within 700 kilometers of the surface. For the first time in history, humans saw Mercury up close. The images were remarkable. Mercury looked superficially like the Moon, grey, cratered, ancient. The surface was covered in impact craters of all sizes, from tiny pits to enormous basins. It looked dead, frozen in time, a record of the violent early solar system preserved in stone. But there were differences. Long, winding cliffs called lobate scarps crossed the surface, cutting through craters and plains alike. These cliffs could be hundreds of kilometers long and several kilometers high, enormous features with no equivalent on the Moon. The scarps were evidence that the planet had shrunk as its interior cooled. As Mercury's core solidified and contracted, the crust was forced to accommodate less volume. The only way to do this was to buckle and thrust, creating the scarps we see today. A giant impact basin, later named Caloris, stretched 1,400 kilometers across, one of the largest impact features in the solar system. Mariner 10 photographed its western half, revealing a complex structure of rings, planes, and radial features. The spacecraft also detected Mercury's magnetic field, the unexpected discovery that continues to puzzle scientists today. The field was weak but unmistakable, generated by processes that shouldn't work on a planet this small and slow rotating. Mariner 10 flew past Mercury 3 times, in March 1974, September 1974, and March 1975. Each flyby provided new data, new images, new discoveries. The spacecraft had its share of problems. The camera's filter wheel stuck. The star tracker had difficulty locking onto guide stars. The tape recorder malfunctioned. Power systems degraded. By the final flyby, Mariner 10 was limping, barely functional. But it delivered. It transformed Mercury from a point of light into a real world, with geography and geology and mysteries demanding explanation. But there was a problem, a big one. Due to orbital mechanics, Mariner 10 could only image one hemisphere of Mercury. Each flyby occurred with the same face of the planet illuminated by the sun. The same half was visible every time. The other half remained completely unknown. When Mariner 10's mission ended in March 1975, we had mapped only 45% of Mercury's surface. Less than half the planet had been seen by human eyes. And then, nothing. For 30 years. Why did NASA abandon Mercury for 3 decades? The answer is simple but frustrating. Mercury is incredibly difficult to reach. You might think that getting to a planet closer to the Sun would be easier than getting to planets farther away. After all, you're falling downhill toward the Sun's gravity, right? The Sun pulls everything toward it. Surely going inward should be easier than going outward. Wrong. This is one of the great counterintuitive facts of orbital mechanics. And understanding it is key to understanding why Mercury was ignored for so long. To understand why, you need to think about orbits, not straight lines. When a spacecraft leaves Earth, it's not starting from rest. It's already moving, orbiting the Sun at about 30 kilometers per second along with Earth. That's our starting velocity, inherited from our planet. To reach Mercury, a spacecraft needs to slow down, to drop into a lower, faster orbit that will take it closer to the Sun. You might think faster and slower are contradictory, but that's how orbits work. Objects closer to the Sun orbit faster. Mercury moves at 47 kilometers per second. Earth moves at 30. To drop down to Mercury's orbit, you first slow down relative to the Sun, fall inward, and then speed up as you approach. The slowing down part is the problem. To change your velocity in space, you need to fire rockets. And to slow down by a lot, you need a lot of fuel. But here's where it gets worse. Simply reaching Mercury's orbit isn't enough. If you want to just fly past, like Mariner 10 did, you can use gravity assists and clever trajectory design. But if you want to orbit Mercury, you need to match its velocity when you arrive. Mercury itself is moving very fast. At 47 kilometers per second, it's racing around the Sun even faster than Earth. When your spacecraft arrives at Mercury after falling inward, it's moving at a different velocity than Mercury, typically much faster relative to Mercury, because you've gained speed falling toward the Sun. To enter orbit, you need to fire your rockets again, shedding all that excess velocity. This requires enormous amounts of fuel. Going to Mercury requires more delta V, more change in velocity, than going to Jupiter. This seems absurd, but it's true. Jupiter is 5 times farther from the Sun than Earth. The journey takes years, and yet, in terms of the fuel required, Mercury is harder to reach. The outer planets are farther away, but their slower orbital velocities make them easier to match. Jupiter moves at only 13 kilometers per second. When you arrive at Jupiter, the velocity difference is manageable. You can use Jupiter's gravity to capture you into orbit, or you can use aerobraking in its upper atmosphere, as we've done at Mars. Or you can simply carry enough fuel for a modest orbital insertion burn. Mercury offers none of these advantages. No atmosphere for aerobraking, weak gravity for capture, and a high orbital velocity that demands massive velocity changes. Let me put this in numbers. To go from Earth orbit to Mars orbit requires a delta V of about 6 kilometers per second. This is well within the capability of modern rockets. We've been sending missions to Mars since the 1960s. To go from Earth orbit to Jupiter orbit requires a delta V of about 9 kilometers per second. More than Mars, but achievable with efficient trajectories and gravity assists. To go from Earth orbit to Mercury orbit requires a delta V of about 13 kilometers per second. More than going to Jupiter, and we're not even counting the orbital insertion burn at Mercury. To actually enter orbit around Mercury, you need a total delta V of about 18 to 20 kilometers per second. This is more than double what's needed for Mars. It's more than going to Saturn. It's comparable to the delta V needed to land on the Moon and return. Mariner 10 solved this problem by not entering orbit. It just flew past, using gravity assists to set up multiple flybys. But a flyby mission can only gather limited data. You race past the planet in hours, snapping pictures and taking measurements, but then you're gone. To truly study a planet, you need an orbiter, a spacecraft that stays with the planet, mapping its entire surface, measuring its properties over time. An orbiter mission to Mercury requires either enormous amounts of fuel or creative trajectory design that takes years to execute. In the 1970s and 80s, neither option seemed feasible. Fuel was expensive and heavy. Every kilogram of fuel meant less room for scientific instruments. The rockets of the era couldn't deliver enough mass to Mercury with enough fuel left over to enter orbit. You could send a small probe that would arrive with dry tanks, or a probe with fuel but no instruments. Neither option was acceptable. And trajectory design was limited by computing power and knowledge. The multi-gravity assist trajectories that would eventually make Mercury missions possible hadn't been fully developed. The math was known, but the practical application, finding trajectories that hit all the right planets at the right times while keeping the spacecraft functional for a decade-long journey, was still emerging. so NASA moved on to other targets. Mars was closer in terms of delta V, and the public was fascinated by the possibility of life. The Viking landers touched down in 1976. Jupiter and Saturn offered spectacular ring systems and dozens of moons. Voyager 1 and 2 launched in 1977, beginning their grand tour of the outer solar system. Venus was relatively easy to reach and scientifically interesting. Soviet missions continued to land on its hellish surface throughout the 1970s and 80s. Mercury, by contrast, offered a small, airless, cratered world that looked superficially like the Moon. It was hard to reach, expensive to orbit, and seemed to promise fewer discoveries than the more dramatic outer worlds. The funding went elsewhere. Mercury waited. But Mercury wasn't forgotten entirely. Scientists continued to study it from Earth, refining their understanding, developing new questions. And in the 1990s, something changed. Radar observations revealed the ice deposits at Mercury's poles, a stunning discovery that raised new questions about the planet's history and volatiles. Improved understanding of Mercury's magnetic field deepened the mystery of how such a slowly rotating planet could maintain a dynamo. New thermal models suggested that Mercury's interior might still be partially molten, challenging assumptions about how quickly small planets cool. And advances in trajectory design opened new possibilities. A mission designer named Chen-Wan Yen at NASA's Jet Propulsion Laboratory developed a trajectory concept that could deliver a spacecraft into Mercury orbit using multiple gravity assists from Venus and Mercury itself. The journey would take years, over 6 years from launch to orbit, but it would require far less fuel than a direct approach. The mission would be called MESSENGER: Mercury Surface, Space Environment, Geochemistry, and Ranging. MESSENGER was approved in 1999. It would end 30 years of silence. MESSENGER launched on August 3, 2004, atop a Delta II rocket from Cape Canaveral. The spacecraft weighed about 1,100 kilograms, more than twice as heavy as Mariner 10. About 55% of that mass was propellant, fuel and oxidizer for the numerous maneuvers required to reach Mercury and enter orbit. MESSENGER was a technological marvel. It carried 7 scientific instruments designed to answer the questions that had accumulated over 3 decades. Cameras for imaging the entire surface, spectrometers for determining composition, a magnetometer for mapping the magnetic field, an altimeter for measuring topography, and instruments for studying Mercury's thin exosphere and space environment. The spacecraft also incorporated innovative thermal design. Operating so close to the Sun, MESSENGER would be exposed to up to 11 times the solar intensity that Earth experiences. Without protection, the spacecraft would have been cooked. Engineers solved this with a ceramic sunshade, a heat-resistant shield that would always point toward the Sun, keeping the sensitive electronics in its shadow. The sunshade was made of ceramic cloth stretched over a titanium frame, capable of withstanding temperatures over 300 degrees Celsius on its sun-facing side, while keeping the spacecraft behind it at room temperature. The solar panels were designed to be tilted away from the Sun, preventing overheating while still generating enough power. The spacecraft could rotate to keep the sunshade pointed correctly, while adjusting the solar panel angles. But before MESSENGER could use any of its instruments, it had to get there. And getting there took 6.5 years. The trajectory was a masterpiece of orbital mechanics. MESSENGER flew past Earth once, Venus twice, and Mercury 3 times before finally entering orbit in March 2011. Each flyby adjusted the spacecraft's velocity, gradually matching Mercury's orbit while conserving precious fuel. Without the gravity assists, Messenger would have needed much more fuel, far more than it could carry. Here's how it worked. When a spacecraft flies past a planet, it can gain or lose velocity relative to the Sun, depending on the geometry of the encounter. By carefully choosing the approach angle and timing, mission designers can use each planet's gravity as a free boost. Messenger's first gravity assist came from Earth 1 year after launch. The spacecraft swung past our planet, gaining velocity and redirecting toward Venus. The 2 Venus flybys came in October 2006 and June 2007. Each one slowed Messenger down and bent its trajectory inward toward Mercury's orbit. Then came 3 Mercury flybys: January 2008, October 2008, and September 2009. Each flyby further refined the orbit, slowing Messenger down and adjusting its trajectory for the final orbital insertion. The Mercury flybys also provided scientific data, offering glimpses of the hemisphere that Mariner 10 had never seen. For the first time, we saw the eastern half of Mercury, revealing new features and deepening the mysteries. The price of this elegant trajectory was time. 6.5 years from launch to orbit insertion. Over 7 billion kilometers traveled, looping around the inner solar system to reach a planet that's never more than 200 million kilometers from Earth. When Messenger finally fired its main engine to enter orbit on March 18, 2011, it became the first spacecraft ever to orbit Mercury. 36 years after Mariner 10's final flyby, we were back. The engine burn lasted about 15 minutes, slowing Messenger by about 860 meters per second. When it was done, the spacecraft was captured, permanently bound to Mercury, ready to begin its scientific mission. And what Messenger found revolutionized our understanding of the innermost planet. Let me tell you about the discoveries. First, Mercury's surface is far more complex than Mariner 10 suggested. Messenger mapped the entire planet for the first time, revealing the hemisphere that had been hidden since the dawn of the space age. The newly visible terrain showed the same cratered landscape, the same lobate scarps, but also unexpected features. Smooth plains covered about 27% of Mercury's surface, regions that had been flooded by ancient lava, similar to the Lunar Maria, but with distinct compositions. These volcanic plains indicated that Mercury had a geologically active past, with magma reaching the surface and reshaping the landscape. Strange hollows dotted the surface, irregular, shallow depressions with bright interiors, found nowhere else in the solar system. These hollows appear to be forming through some kind of sublimation process, where volatile materials escape from the rock under the intense solar radiation. What those volatiles are remains debated. The Caloris Basin, first glimpsed by Mariner 10, was mapped in its entirety. Messenger revealed that the basin floor had been flooded by lava after the impact, creating smooth plains surrounded by the rough, chaotic terrain of the original crater. Second, Mercury's core is even stranger than we thought. Messenger's gravity measurements revealed that Mercury's core is not only enormous, but partially liquid. The outer core remains molten, despite Mercury's small size and ancient age. This liquid outer core is what generates the magnetic field, but exactly how remains unclear. Even more surprising, Messenger found evidence for a solid inner core within the liquid outer core, similar to Earth's structure, but proportionally much larger. The inner core may be iron-sulfur alloy, with a composition that allows it to remain solid at Mercury's relatively modest internal temperatures. The core structure suggests that Mercury's interior is more complex than simple models predicted. Heat loss, core crystallization, and dynamo generation are all intertwined in ways we're still working to understand. Third, Mercury is shrinking. The lobate scarps that Mariner 10 first observed are thrust faults, places where the crust has buckled as the planet contracted. Messenger mapped thousands of these features, revealing that Mercury has shrunk by about 14 kilometers in diameter since its formation. This shrinkage is caused by cooling. As Mercury's interior loses heat to space, the core solidifies and contracts. The contraction causes the crust to compress, buckling into the scarps we see today. Earth has plate tectonics to accommodate internal stresses. Mercury has no plates. Instead, the entire crust acts as a single shell, crumpling as the planet shrinks. The scarps are wrinkles on a shrinking world. Fourth, the polar ice is real and extensive. Messenger confirmed the radar observations with direct measurements. The polar craters contain water ice, covered in some areas by a thin layer of dark organic material. The ice deposits are found exactly where they should be, in permanently shadowed regions where temperatures never rise above -100 degrees Celsius. The amount of ice is substantial. Estimates suggest trillions of kilograms, enough to cover Washington, D.C. in a layer 2.5 miles thick. For a planet so close to the Sun, this is remarkable. Fifth, Mercury's composition is strange. The surface contains unexpectedly high levels of volatile elements: sulfur, potassium, sodium, chlorine. These elements should have been driven off by the intense heat near the Sun. Their presence suggests that Mercury formed from materials different from those that formed Earth and the Moon, or that it formed in a different location and migrated inward. The iron-poor surface, combined with the iron-rich core, deepens the mystery of how Mercury came to be. Some process, giant impact, solar heating, unusual formation conditions, created a planet unlike any other in the inner solar system. Messenger operated for 4 years in orbit, far exceeding its planned 1-year mission. But eventually the spacecraft ran out of fuel for the orbital maneuvers needed to maintain its trajectory. On April 30th, 2015, Messenger crashed into Mercury's surface, creating a small crater on the planet it had spent years studying. It was a fitting end, the spacecraft becoming part of the world it had revealed to us. But the exploration of Mercury didn't end with Messenger. Even as Messenger was orbiting Mercury, the European Space Agency and the Japanese Aerospace Exploration Agency were developing a new mission, BepiColombo. Named after Giuseppe BepiColombo, the Italian scientist who first proposed the gravity assist trajectory that Mariner 10 used, BepiColombo is the most ambitious Mercury mission ever attempted. The mission consists of 2 orbiters, the Mercury Planetary Orbiter, built by ESA, and the Mercury Magnetospheric Orbiter, built by JAXA. Together, they carry 16 scientific instruments, more than twice what Messenger carried. The European orbiter will focus on the planet itself, its surface, interior, composition, and evolution. It carries high-resolution cameras, spectrometers spanning from infrared to X-rays, an altimeter for mapping topography, and instruments for probing the interior. The Japanese orbiter will focus on Mercury's space environment, the magnetic field, the magnetosphere, the exosphere, and the interaction with the solar wind. It carries magnetometers, particle detectors, and plasma instruments designed to understand how Mercury's weak magnetic field interacts with the intense solar wind at Mercury's orbit. Together, the two spacecraft will provide a complete picture of Mercury that neither could achieve alone. The synergy between surface science and space science is crucial for understanding a planet where the boundary between surface and space is so thin. BepiColombo also carries a Mercury transfer module, which provides propulsion during the cruise phase. This module has 4 ion engines, highly efficient thrusters that use electrical energy to accelerate xenon gas to high velocities. Ion engines produce much less thrust than chemical rockets, but are far more fuel efficient, making them ideal for the long journey to Mercury. The ion engines allow BepiColombo to carry more scientific payload and use more direct trajectory than Messenger. Instead of relying solely on gravity assists, BepiColombo uses its ion engines to continuously adjust its trajectory, reducing the total flight time and providing more flexibility. Still, the journey is long. BepiColombo launched on October 20th, 2018. Like Messenger, it requires multiple gravity assists. The spacecraft will fly past Earth once, Venus twice, and Mercury 6 times before finally entering orbit in December 2025. 7 years from launch to arrival. 7 years of patient trajectory corrections, gravity assists, and ion engine burns. 7 years of waiting before the science can truly begin. As of now, BepiColombo has completed several of its Mercury flybys, sending back stunning images that preview what's to come. Each flyby brings the spacecraft's orbit closer to Mercury's, setting up for the final approach. The images from the flybys have already revealed details that Messenger couldn't capture. Different lighting angles, different viewing geometries, and improved camera technology have shown familiar features in new ways and hinted at discoveries to come. When it enters orbit, BepiColombo will study Mercury in unprecedented detail. The two orbiters will work together, one focusing on the planet's surface and interior, the other on its magnetic field and space environment. The mission is planned for at least 2 years of science operations, with a possible extension. In that time, BepiColombo will map Mercury's surface at a higher resolution than ever before, probe its interior with unprecedented precision, and monitor its space environment through the full range of Mercury's highly elliptical orbit. BepiColombo will answer questions that Messenger couldn't. Why does Mercury's magnetic field have the structure it does? What is the detailed composition of the surface? How does the solar wind interact with the planet? What can Mercury tell us about the formation and evolution of rocky planets? And it will surely raise new questions. That's the nature of exploration. Each mission answers what came before, while revealing what comes next. The 30-year gap is long closed. Mercury is now a priority for planetary science, its mysteries recognized as fundamental to understanding how planets form and evolve. Let me step back and tell you why Mercury matters. Mercury is the only rocky planet besides Earth with a global magnetic field. Studying it helps us understand how planetary dynamos work, knowledge that applies to Earth, to exoplanets, to the cosmic question of which worlds might be habitable. Mercury experienced the same late heavy bombardment that scarred the Moon and probably brought water to Earth. Its craters are a record of that violent era, preserved without the erosion and tectonics that have erased evidence on Earth. Mercury's extreme conditions, Scorching heat, freezing cold, minimal atmosphere, intense radiation. Test our understanding of planetary processes. If we can explain Mercury, we can explain a lot about planets in general. And Mercury's density, its composition, its orbital position, all provide clues about the formation of the inner solar system. Understanding why Mercury is so strange helps us understand why Earth is the way it is, why we have the conditions that allow life. Mercury isn't just the forgotten planet, the neglected world, the 3-decade gap in our exploration. Mercury is a key to understanding planetary science itself. Let me tell you about Mercury's day. Mercury has the strangest day-night cycle of any planet in the solar system. One Mercury year, one orbit around the Sun, takes 88 Earth days. One Mercury day, one rotation on its axis, takes 59 Earth days. These two periods are locked in a 3-to-2 resonance. For every 2 orbits Mercury makes around the Sun, it rotates exactly 3 times on its axis. This resonance is stable, maintained by tidal forces from the Sun. This 3-to-2 ratio is not a coincidence. When Mercury's rotation was faster, tidal forces from the Sun gradually slowed it down. But instead of locking into a 1-to-1 resonance, like the Moon with Earth, where one face always points toward the central body, Mercury settled into this more complex pattern. The 3-to-2 resonance is stable because of Mercury's elliptical orbit. At perihelion, when Mercury is closest to the Sun, it moves fastest in its orbit. At aphelion, when it's farthest, it moves slowest. This varying orbital speed interacts with the planet's rotation in a way that stabilizes the 3-to-2 pattern. But here's where it gets weird. Because of this resonance, a solar day on Mercury, the time from one noon to the next, takes 176 Earth days. That's 2 Mercury years. That's longer than the planet's year itself. Let me explain this, because it's genuinely counterintuitive. On Earth, a solar day is the time from one noon to the next noon, the time it takes for the Sun to return to the same position in the sky. For us, this is 24 hours, slightly longer than the time it takes Earth to rotate once on its axis, which is about 23 hours and 56 minutes. The difference is because we're also orbiting the Sun, so we need to rotate a little extra to bring the Sun back to the same position. On Mercury, this effect is extreme. Mercury's slow rotation and fast orbit combine to create solar days that span 2 entire years. If you stood on Mercury's surface, you would experience one sunrise, then wait almost 6 Earth months for the next. The Sun would crawl across the sky, taking months to rise, months to set. Day and night would stretch across seasons on Earth. You could have breakfast, go to sleep, wake up, live for weeks, and the Sun would still be in roughly the same part of the sky. The concept of morning and afternoon would span months. And during that long day, the Sun would do something strange. At certain points on Mercury's surface, the Sun would appear to rise, stop, reverse direction, and then continue rising. This happens because Mercury moves fastest in its orbit when it's closest to the Sun, temporarily outpacing its rotation. The Sun appears to move backward in the sky before resuming its normal motion. This effect is called apparent retrograde motion, and it's unique to Mercury in our solar system. Imagine watching that. The Sun rises above the horizon. It climbs slowly, taking days to move noticeably. Then it stops. It starts to descend again, as if changing its mind, moving backward the way it came. And then it stops again, finally climbing for good, continuing its months-long journey across the sky. At certain longitudes on Mercury, called hot longitudes, the Sun is directly overhead at perihelion, when Mercury is closest to the Sun and receiving maximum radiation. At other longitudes, warm longitudes, the Sun is overhead at aphelion, when Mercury is farther from the Sun. The hot longitudes receive about 2.5 times as much solar radiation as the warm longitudes. This creates a permanent pattern of thermal extremes across Mercury's surface. This is real. This happens on Mercury. The physics of orbital mechanics and tidal locking create a day unlike anything we could experience on Earth. Let me tell you about the temperature extremes. Mercury's surface experiences the largest temperature swing of any planet in the solar system. On the sunlit side, temperatures reach 430 degrees Celsius. At this temperature, lead melts, zinc melts, tin melts. The rocks glow with infrared radiation, radiating heat back into space. You could melt a block of lead simply by leaving it in the Mercury sunlight. To put this in perspective, your oven at home maxes out around 250 to 300 degrees Celsius. Mercury's surface, at its hottest, is nearly twice that temperature. It's hot enough to melt many metals, hot enough to vaporize some compounds, hot enough to destroy any spacecraft that isn't specifically designed to survive. On the dark side, temperatures plunge to minus 180 degrees Celsius. This is colder than any temperature ever recorded on Earth's surface, colder than the night side of the Moon, cold enough to freeze carbon dioxide solid. At this temperature, oxygen would be a liquid, nitrogen would be close to freezing. The swing from hot to cold is over 600 degrees Celsius. No other planet experiences anything like this. Mars has temperature swings of about 100 degrees between day and night. The Moon has swings of about 300 degrees. Mercury nearly doubles even the Moon. Why such extremes? Because Mercury has no atmosphere to distribute heat. On Earth, our atmosphere acts like a blanket and a conveyor belt. It absorbs heat from the Sun, distributes it around the planet through winds and ocean currents, and releases it slowly at night. The atmosphere holds on to heat, moderating the temperature extremes. Even the hottest deserts cool significantly after sunset because the air retains heat and redistributes it. Even the coldest regions warm during the day because warm air flows in from elsewhere. The atmosphere connects every part of Earth's surface, sharing energy, smoothing out extremes. Mercury has virtually no air. Each patch of surface is alone with the Sun. When sunlight hits, the surface absorbs the energy and heats up. When the Sun sets, a process that takes months, remember, the heat radiates away into space with nothing to hold it in. There's no wind to carry heat from the day side to the night side. There's no atmosphere to trap infrared radiation. There's no ocean to store and transport energy. The only thing connecting the hot and cold sides is the rock itself. Heat conducts through rock, but slowly, far too slowly to moderate the extreme temperatures. The thermal conductivity of rock is low, and the distances are large. Each location on Mercury swings from oven to freezer over the course of its long day. And yet, in the permanently shadowed craters at the poles, ice survives. Protected from direct sunlight for billions of years, These regions maintain temperatures cold enough to preserve water ice indefinitely. Mercury is a planet of contradictions. The hottest and coldest surfaces in the inner solar system, separated by just a few kilometers. Fire and ice coexisting on a world that seems too small and too close to the sun to harbor either extreme. Let me tell you about Caloris Basin. Caloris Basin is one of the largest impact craters in the solar system, about 1,540 kilometers in diameter. It was created by an asteroid or comet impact approximately 3.9 billion years ago, during the Late Heavy Bombardment. The Late Heavy Bombardment was a period of intense cratering that affected all the inner planets and moons. Around 4 billion years ago, gravitational interactions between Jupiter and Saturn may have destabilized the asteroid belt and scattered comets from the outer solar system, sending a rain of debris cascading through the inner solar system. Mercury, with its weak gravity and proximity to the Sun, couldn't deflect this bombardment. It took the full force of the Late Heavy Bombardment, accumulating the craters we see today. The Caloris impact was one of the largest. The energy released was equivalent to trillions of nuclear weapons. The asteroid itself was probably about 100 kilometers across, traveling at tens of kilometers per second. When it struck Mercury, the impact vaporized the asteroid instantly. A shock wave rippled through the planet. Rock was melted, pulverized, ejected. The crater excavated material from deep within Mercury's crust, perhaps even reaching the mantle. The name Caloris comes from the Latin word for heat. The basin was named because it's located at one of Mercury's hot longitudes, a region that receives maximum solar radiation when Mercury is closest to the Sun. But the most remarkable effect was on the opposite side of the planet. Directly antipodal to Caloris Basin, on the exact opposite point of Mercury, there's a region of chaotic, jumbled terrain called the weird terrain, or chaotic terrain. This terrain was created by the Caloris impact. Seismic waves from the impact traveled through Mercury, converging on the opposite side. When the waves met, they reinforced each other, shaking the surface violently. Hills were jostled, craters were disrupted, and the terrain was scrambled into a chaotic jumble. Think about that. An impact so powerful that it literally scrambled the ground on the opposite side of the planet. The energy was so immense that it didn't just affect the impact site, it affected the entire globe. The Caloris impact was so powerful that it scrambled the ground on the opposite side of the planet. This gives us insight into just how violent the early solar system was, and how dramatic the events that shaped Mercury must have been. Mariner 10 discovered the weird terrain, but only saw part of it because the region was near the terminator, the line between day and night, during the flybys. Messenger mapped it completely, confirming its connection to the Caloris impact and revealing details that Mariner 10 couldn't capture. Let me tell you about what we still don't know. Despite 2 spacecraft missions and decades of Earth-based observation, Mercury remains mysterious. We still don't fully understand why Mercury's core is so large. The giant impact hypothesis is plausible, but unproven. We have no direct samples of Mercury's rocks to analyze their composition and test the models. We still don't understand how Mercury maintains its magnetic field. The slow rotation should prevent an effective dynamo. Something unusual about Mercury's core, perhaps its composition, perhaps the way it crystallizes, perhaps something we haven't considered, allows the field to persist. We still don't know the exact composition of Mercury's surface. Messenger provided clues, but the instruments had limitations. BepiColombo will provide better data, But even that may not answer all questions. We still don't know Mercury's full geological history. The volcanic plains suggest an active past. But when did volcanism end? What triggered it? How did Mercury's interior evolve over 4.5 billion years? We still don't know if Mercury formed where it is today or migrated from elsewhere in the solar system. Its composition is unusual for its location. Perhaps it formed farther from the Sun and moved inward. Perhaps it formed closer and was altered by processes we don't understand. Mercury is a small planet, but it contains big mysteries. Every answer raises new questions. Every discovery deepens the puzzle. This is why NASA's 30-year gap matters. For 3 decades, these questions went unanswered. For 3 decades, Mercury's mysteries accumulated, waiting for someone to return. And when Messenger finally arrived, it found a planet stranger than anyone expected. The answers it provided only showed how much we still had to learn. Now, BepiColombo is continuing the work, and perhaps future missions, landers, sample returns, long-term orbiters will follow. Mercury won't be ignored again. Let me tell you about the future. BepiColombo will arrive in orbit in late 2025, beginning a comprehensive study that will last at least 2 years. Its 2 orbiters will provide complementary data, one studying the planet itself, the other studying its magnetic field and interaction with the solar wind. But BepiColombo is just the beginning. Scientists are already discussing future missions. A Mercury lander could directly sample surface rocks, providing compositional data that remote sensing can't match. The technical challenges are immense. The extreme temperatures, the long day-night cycle, the lack of atmosphere for parachute descent, but not insurmountable. A sample return mission would be even more ambitious. Bringing Mercury rocks to Earth for laboratory analysis would revolutionize our understanding of the planet's formation and evolution. But the delta-V requirements for returning from Mercury are even higher than getting there, making such a mission extremely challenging. A network of surface stations could monitor Mercury's seismic activity, revealing the structure of its interior in ways that orbiting spacecraft cannot. Seismology has been transformative for understanding Earth, the Moon, and Mars. Applying it to Mercury could answer questions about its core structure and ongoing shrinkage. For now, these missions remain concepts, ideas discussed at conferences, written up in proposals, awaiting funding and technical development. But the precedent has been set. Mercury is no longer the forgotten planet. It's a world worthy of exploration. Let me bring this back to the central question. Why did NASA ignore Mercury for 30 years? The answer, as we've seen, is complex. It's not a simple story of neglect or disinterest. It's a story of priorities, technical challenges, and the limits of technology at a particular moment in history. Mercury is hard to reach. The orbital mechanics require either enormous fuel or years of patient gravity assists. In the tight budgets of the post-Apollo era, missions that seemed cheaper and faster took priority. NASA had limited resources, and those resources went to missions that promised more science per dollar. Mercury seemed less exciting. A small, cratered, airless world, no possibility of life, no dramatic rings or colourful clouds, just rock and sun and silence. The public wasn't captivated, and public interest drives funding. This was partly unfair. Mercury is scientifically fascinating. We know that now. But in the 1980s, The mysteries that make Mercury so compelling weren't fully appreciated. The polar ice hadn't been discovered. The magnetic field puzzle wasn't fully understood. The questions that would draw scientists back to Mercury were still being formulated. Mercury's science wasn't fully appreciated. Before Messenger, we didn't know about the bizarre magnetic field structure, the complex core, the volcanic history, the ice deposits. Mercury seemed simpler than it turned out to be. Scientists had questions, but they didn't have the data to show how important those questions were. And space exploration involves choices. You can't go everywhere at once. Priorities must be set, and Mercury wasn't the priority. Mars offered the possibility of life. Past or present, it didn't matter. The search for life is the most compelling narrative in space exploration, and Mars had it. The outer planets offered spectacle and discovery. The rings of Saturn, the moons of Jupiter, the auroras and storms, and alien landscapes that captivate audiences. Mercury was left for later. But later turned out to be 30 years. In that time, technology advanced. Computers became powerful enough to calculate complex multi-gravity assist trajectories. Ion engines became practical, offering efficient propulsion for long missions. Spacecraft became more capable, able to carry more instruments while using less fuel, and scientific questions accumulated. The polar ice discovery in the 1990s was a wake-up call. The magnetic field puzzle deepened as theoretical understanding improved. Planetary scientists began to realize that Mercury wasn't just a bigger moon, it was a unique world with unique lessons to teach. Eventually, Mercury became impossible to ignore. Messenger answered many questions and raised many more. BepiColombo will answer some of those and raise still more. The cycle of discovery continues, question leading to answer, leading to new question. Mercury is no longer forgotten. It's recognized as a key to understanding planetary formation, magnetic field generation, and the evolution of rocky worlds. Its extreme conditions and strange properties make it a natural laboratory for testing our theories. The 30-year gap was a loss, a period when we could have learned so much but didn't. But perhaps it was also necessary. Perhaps we needed the technology, the questions, the maturity as a spacefaring species to truly appreciate what Mercury had to offer. Now we're ready. Now we're exploring. Now we're uncovering the secrets of the smallest, strangest planet in our solar system. And the secrets are magnificent. Mercury, the messenger of the gods, finally has messages to deliver. We just had to wait to receive them. Thank you for watching. If this video changed how you think about Mercury and planetary exploration, consider subscribing. We explore the strangest worlds in the solar system and the mysteries they contain. The universe is full of secrets. Mercury holds some of the most profound. And the next time you glimpse Mercury low on the horizon, just after sunset or before sunrise, remember, you're looking at one of the most difficult destinations in the solar system, a world that took 30 years to revisit, and a planet that continues to surprise us with every new discovery. That tiny point of light contains ice at its poles and fire on its surface. It has a magnetic field that shouldn't exist, and a core that's too big to explain. It spins so slowly that the sun moves backward in its sky, and its days last longer than its years. Mercury is strange. Mercury is wonderful. Mercury is waiting. And so is the future. See you in the next video.